And the recording has started, so I'll try again. Welcome everyone to the SIG OpenXLA community meeting. Next slide. Thank you. And just, for those of you who are new, and also for those of you who have been with us, wanted to restate the goal of this initiative and this project. We're building an open state-of-the-art ML compiler ecosystem collaboratively with hardware and software partners using the best of XLA and MLIR. Next slide, James. So we usually kick off these meetings inviting the new members to this meeting to introduce themselves, and so we can welcome you to the community. Is there anyone new with us today?
At least
hello?
2 people.
Yes, hello.
Hello. So I'm Mikhail Dvoretsky from Intel. I was mostly invited here for, I think, the second topic, the GmlSt overview, because I'm currently looking into that for tiling GPU workloads.
Awesome. Welcome, Mikhail.
Hi, also on the line is Alex Gerbic, so that's me. I'm a VP of software at Untether AI. We're a semiconductor AI inference accelerator company, and we're thinking about next generation software and interested in this initiative. So with me is also a colleague, Josh. You on the line?
Yep, I'm here. Hello all, I'm Josh Fender. Work with Alex as a principal engineer here in our software organization. I'm always on the lookout for good ML compiler technology that can help us move forward. And that's what I hope you guys have here. So hello all.
Hi, and welcome both of you. So glad to have you here. Anybody else who would like to introduce themselves today?
I can introduce myself. I'm Frederik, and I'm from Google, and this is the first time I'm joining the meeting. And I'll do the GmlSt stuff. We also care about GPU loads.
Awesome. Thanks for signing up to present, Frederik.
I'm Alex, and this is Oleg and Mohammed. We're part of XLA team. We work also with Frederik on GmlSt. So we are based in Munich and working on tiling and Fusion mostly.
Awesome. Thank you for joining. Anyone else? And in the interest of time, I'm going to move on now, but if we missed anyone, please feel free to add your introduction to the chat.
Sorry, I can introduce myself.
No worries, please go ahead.
So I'm Jaya Shankar from NVIDIA, kind of leading the XLA initiative here.
Awesome, welcome. Okay, so just a bit of housekeeping at the top of this meeting. Our meetings happen monthly on Zoom on the 3rd Tuesday at 8 a.m. Pacific time. Pacific time will change for us next month. So I'm still gonna figure out what that means for those of us not in the US with standard time zones. So we have a rotating meeting host and scribe. I assume today Josh will be scribing. James will be scribing. Is that correct, James? Okay. And we'll also have the agenda shared by the host of the meeting a week prior to these meetings in GitHub discussions, where, no worries, where our primary community level discussions are taking place. We'll also share the meeting minutes and slides tomorrow in the meetings archive in the community repo in GitHub. And generally, these meetings cover development updates, any active design proposals, and any community topics under discussion. Next slide. So here's an overview of our collaboration channels. These are a little bit in flux. The important things to note is that as much as possible, we're hoping to have public design conversations that are legible and accessible to the community. Right now, community discussions are happening on the community repo in GitHub discussions. Technical discussions for XLA are a little spread between issues, PRs, GitHub discussions, and then for StableHLO, I believe they're leveraging issues and PRs pretty heavily. And we'll work on standardizing that as we go, just trying to feel out what makes most sense to the community. Discord is a great place to visit for synchronous discussions. And of course, we have these community meetings. Next slide. And so now we'll dive into our development updates. We have 3 presentations today, and we've shared the slides with you already. But again, these will be accessible both in videos on YouTube and also PDF slides on the GitHub repo. So I believe the first person to kick us off is Kevin.
Yes, hello.
Awesome.
Cool. So I'm Kevin Gleason. I'm with Google, and I'll be talking about StableHLO compatibility. We have a goal of offering long-lasting and portable MLIR artifacts via StableHLO. So agenda for today, from a high level, we're going to talk about what are the compatibility guarantees, how we're going to maintain them, and then we have a prototype, and then we'll talk about what work is left to do before we hit a v1.0 state of these guarantees. Next slide. Cool. So from a high level, our current before I get into this, I want to emphasize that all of this work is still in the RFC phase. It's very use case driven. So if anybody in here has use cases for portable artifacts, we are very interested in hearing them. There's a link in the bottom right here for feedback. Taya mentioned that we were using pull requests. That's our primary means. So feel free to lead feedback on there at any time. So our primary requirements are 6 months of backward compatibility and 3 weeks of forward compatibility. This graphic at the bottom here attempts to illustrate that. Basically, if you serialize an artifact, it is guaranteed to be deserializable at a version 6 months in the future. And then forwards compatibility when possible, really when no new semantics have been introduced in a version. Then we will offer 3 weeks of forward compatibility. So that v3 artifact on the right is deserializable in the version 3 weeks prior, v2. And then the third requirement there is aspirational. It's a nice to have. It's for API stability. We haven't had too many strong use cases for this, but basically this would mean if you update your revision of StableHLO, you might have to fix up a few call sites, but that should have no impact on the actual portability of the binary artifacts. There was a question in chat for why not state in terms of versions rather than time. That's an interesting bit of feedback that's worth considering. The rationale for considering time is that it's largely based around update schedules of various use cases. So making sure that if different devices are running slightly different versions, that they will be able to communicate with each other properly.
I will just offer that let's collect the questions in the chat and then address them in the Q&A section, just so we can preserve the flow. Cool. Sound good, Kevin?
Okay. That sounds good. Good for next slide. I'm not going to spend too much time on this, but this is also in that same pull request 115. These are the proposed supported dialects, operations, attributes, and types. Again, highly use case driven. If anything that is a requirement for one of your teams that is not here, we would be very interested in hearing that as feedback on that pull request. Next slide. Cool. So the mechanisms for maintaining compatibility are upgrades and downgrades. Talk about IR upgrades first. This is our means for providing backward compatibility. As I mentioned, we were providing our current proposal is for 6 months of backward compatible support. Looking at the sort of code examples here, this would be an example of if we wanted to rename an operation from sub to subtract. There's various comparable things like this that have happened in dialects over time. So it's a very valid example to look at, something that would break MLIR code. So on the right here, we would have this v39 that has sub, and we would be able to provide machinery that allows you to upgrade it to this hypothetical version 40. And on the right, you see in the blue that it says StableHLO subtract. So as long as we have this upgrade hook, then this artifact created in v39 would be fully deserializable and runnable in v40. And since these payloads have a version number, 39 and 40, etc., our tooling would be able to tell you if a file is out of the compatibility window, or if it's inside of it, it should be guaranteed that it's deserializable. Next slide. And downgrades are just the opposite. This would be our means of providing forwards compatibility. Again, since we have these version numbers attached, we can warn if something is created at a producer version that's too high for the consumer to handle. So we would be able to tell what version you need to upgrade to run it. We had mentioned that it's 3 weeks of forwards compatibility for dialect changes. This is really useful for when a dialect evolves in a semantically compatible way. So renames are a good example of this, looking at the same one. For 3 weeks in that version 40, when you serialize the MLIR, we would actually be producing the StableHLO sub on the right there. So that artifact on the right is fully runnable in version 39, and as we showed on the previous slide, fully deserializable and upgradable in version 40. So this is a means of forwards compatibility. Next slide. So these are, as I mentioned, we have a prototype. This is in the works. There's a pull request open for this as well. I just wanted to give a high level of the sort of tooling and APIs that we'll be offering. The first one is this StableHLO Compat tool, which has a flag to specify the target version. It defaults to maximize the forwards compatibility window. So it would default to the minimum supported version. But you could also target the current version if you want. If you had an old artifact and you wanted to upgrade it to create a new artifact in the current version of libStableHLO. So that could be super useful for just maintaining up-to-date artifacts. The second flag is more of a debug tool, emit assembly. Reason I'm including this in this presentation is just to say we're building all of these compatibility guarantees on top of a recently released MLIR bytecode format. And the rationale for that is the bytecode has stability aspirations, whereas the textual assembly format has no guarantees over time. And additionally, there's more intricacies to bytecode deserialization that allow us to get clever and maintain more compatibility over time. I detailed more of those in that original 115 pull request. So if there's any interest in that, take a look at the request. Second is the APIs. Currently, the pull request only offers a way to parse a file that has compatibility and return the top level operation, as well as a means of writing to a stream. Next slide. So what would implementing upgrade and downgrade hooks look? Just for the sake of example, this is that exact same sub renames to subtract. You can see we have a call to add upgrade, which would take anything from less than version 40 and upgrade it to v40. And we provide a hook for StableHLO.sub, and you can see it just calls a rename to subtract. This operates on generic operation pointers because, especially in the case of renames, there's no guarantee that an operation still exists in the dialect. And this is a good and very flexible way to provide upgrades and allow you to evolve the dialect without having to maintain all of the sort of cruft and outdated constructs. And then the downgrade looks very similar. It latches onto subtract and then renames it back to sub. Next slide. Cool. So this is just the example of using the tool that I described a few slides ago. We have this serialized file, sub.mlir, and if we were to look at the assembly for it, we can see that it's at a compatibility version of 37, which would mean that it has the sub operation prior to its renaming. The second one, we are targeting version 40. That's the most up-to-date version, and we can see that it generates MLIR code that is up to date. So we were actually able to take an old file and bring it into the current version of libStableHLO. So now that artifact has 6 months of compatibility guarantees from its current creation date. And then the last one example there is we want to provide forwards compatibility back for version 38, and we can see that we take that file, it gets upgraded, and then we are able to re-downgrade it back to StableHLO.sub. You'll notice that the final example here is also in fully generic format. This is because StableHLO.sub doesn't exist at version 40, and so we're producing invalid IR technically if upgrades didn't exist. This is sort of another reason to use the bytecode format, is that it's produces effectively identical artifacts with the upgrades and downgrades because it is always operating on the generic IR structure. And next slide. So lastly is just what work is left to do. This is sort of the Q4 2022 plans. I mentioned that bytecode format has the MLIR bytecode format has aspirations for stability. We still need to hammer out what that actually means, and so we want to get discussion with upstream MLIR started regarding creating a stable bytecode format. That's a requirement for us to build on top of this bytecode format. Next is sort of an ease of life sort of thing, makes this easier to implement, and it might be beneficial to other dialects as well, but starting a discussion about stability and compatibility guarantees in the built-in dialect. This is where most of the types and attributes that we provide guarantees for will be coming from. And so if there were stability there, then there would be a whole lot less for StableHLO to have to maintain. And then the final one is our compatibility tools in a prototype. We want to make it just a fully production ready with better error handling and better messages and whatnot. And at the end of that, we will hold the design review to ensure that it upholds the entirety of the StableHLO compatibility RFC that we mentioned. Last note here is just that we aim to have a working solution by the end of Q4 this year. And that leaves us with Q&A. Yeah, so I mentioned the answer to that, time instead of versions. To Mehdi's point, yeah, so there's one of the things in the RFC Mehdi had mentioned here that we need to have some sort of versioning to have solid compatibility guarantees. And one of the things from the future RFC work that we want to do is talk about what would constitute a version of this tooling. It could be a weekly release, it could be less, it could be more, but again, this is entirely use case driven, so we are interested in hearing what use cases are out there.
Like a release is basically like a tag on a commit, more or less, right? So it's a stake in the ground, which I think are important, because if you're at the top of the tree, that 3-week window makes sense, right? But if you're on a version of TensorFlow that's has a version of OpenXLA or in it, right, and then you're frozen there, maybe we need some tags or something in order to light the way, right? Because quickly you'll be out of that 3-week window before you know it, right? And for compatibility reasons, we'll need to have some sort of tagging or versioning to light the path, I think. So not everybody uses top of tree or 8 is able to, right, build everything and then put it into service, if that makes sense.
Yeah, absolutely. And it could just be the schedule with which we integrate this project into MLIR HLO, or again, just tagging releases, but the frequency of tagging should be relatively consistent and predictable.
Yeah, right. I think it'll be just a matter of like having a known predictable way of doing the tags or releases, for sure.
Yep. Cool. Yeah, and thanks for pointing that out. That's again, work that still needs to be done. And looks like that's the end of the questions.
I had a question about your serialization format. So one use case that we've had run into in the past is, let's say we ship a product with version 3, and then version 4 comes out, which we don't have time to upgrade, but we would like to read version 4 so we would like to read version 4 files with the V3 product that we're shipping. So what that means is that if there are operators in version 4 that are the same, then we should be able to read them into V3 IR in memory. So that's the forward compatibility requirement that's important for products. If you're in development, it doesn't matter, because we can keep changing versions as long as we're in development. But when we ship something, then it takes more time for us to go to V4, let's say.
Yeah, right. And that's sort of exactly the driving use case for forward compatibility. And as you mentioned,
it should not require a same format. We should just make sure that the V4 reader can actually produce V3 IR in-memory file for things that are defined in V3.
Yep, exactly. And if V4 uses some new constructs, we're actually able to warn and let you know exactly what's not usable on V3.
So in V3, that'll generate an error if you're reading a file that is not supported, some IR that is not supported in V3. Right. Okay. I think we're on the same page. I just wanted to clarify.
Cool.
I mean, perhaps it's important to also just differentiate between the file format and the offsets. So like if there's a different format of the files versus like different offsets that are unsupported, I think we run into different issues here. So I think that the point about like if you have a file written at a newer version but only using ops from version 3, being able to read it, that's true as long as for a fixed format of the file effectively.
So I think that is true, but I think there's a stronger requirement on the reader for if you want to support. So even if so, one way to do this would be to keep the format same and just keep adding extension, or you can change the format, but you have to be able to recover the old semantics or old IR. Those are the two ways.
Agreed.
All right, I think we have one other question in chat. Has that been addressed yet? From Jackie.
Oh, there we are. Did they cascade or are they planned to be flattened? Currently, the way it's implemented is in a cascading manner. That's the way the prototype does it. And there's an example in the compatibility tool pull request of a cascading example. But really, it's more of a, as long as you can upgrade from the version prior to the version that the hook was created for, it should be able to cascade correctly.
Great, thank you so much, Frederik. Next up is, oh, sorry, thanks, Kevin. Next up is Frederik. And Frederik, do you want to take things off?
Sure. Hi, everyone. I'm Frederik. I work at Google on the GPU CPU codegen team, mostly on tiling and fusion at the moment in the context of GPU codegen. And this is joint work with Stefan and Alex, who are on the call as well, and also with Adrian, who's not here today. Yeah, so, and this is structured in two ways. I'll talk generally about GmlSt, and then there's a couple of slides with examples, and we'll see how many of those we get to do. But if you're interested, you can just look at them by yourself later or ask questions. So tiling and fusion in general. So the goal is to break operations down to tiles, and that is to make better use of the cache on the CPU, for example, or to map nicely to device-specific concepts. Examples, there are blocks or warps on the GPU or on the CPU vectorized instructions. And just so we're clear on the terminology, I'll refer to tiling as breaking an operation down into subsets or tiles and process them separately. That involves creating the loop structure or the loop nest and then the tiled implementation within that. And fusion, I refer to as pulling producers of inputs into an already tiled implementation. So pulling producers into an already tiled loop nest, for example. And then another interesting thing is how's all of this different from the tiling and fusion implementation in XLA today. This is moving to a tile-based fusion and code emission instead of point-wise how it is done in XLA today. So XLA would today point-wise emit the code and do scalarized code emission essentially. And we aim to do that on a tile-based way, even nested tiles. And we actually even aim to be future-proof with regards to other kinds of subsets that are not necessarily tiles. Next slide. This is an overview of how the pipeline works today. This is a GmlSt-based tiling and fusion pipeline. We start off with, and we'll see examples shortly. We start off with tileable operations. This is a destination style equivalent of HLO operations. So they can be linear operations, but they can also be THLO operations, or any operation really that is destination style and implements the tiling and fusion interfaces. So if we tile these operations and fuse them, then we end up with loops and loop nests. And within those loop nests, we'll typically have tileable operations again, just smaller tileable operations. And if we're lucky and these are on small static shapes, we can at that point apply scalarization or vectorization. And then we have vectorized code or code that operates on scalars. But the loop nest remains as it was before. And we also very likely still have tileable operations within that. And at that point, we have to address the still tileable operations that operate on dynamically shaped inputs or just big inputs. And those have to be bufferized. That is what one-shot bufferization does today. And after that's done is essentially the same code as before, just operating on buffers instead of tensors at that point. And when we reach that point, we can apply very custom patterns to implement GPU-specific algorithms for reduction or CPU-specific algorithms, or we can also lower these things to custom calls into libraries that have efficient implementations already. Next slide. This summarizes a few design goals in GmlSt or some characteristics that are specific to GmlSt that we care about. As nested tiling, we want to be able to have multiple levels of tilings. One example there is on the GPU to be able to tile things to blocks, to warps, and to threads. But this also applies to other devices on the CPU. We also want to be able to tile things to match the cache sizes and then to tile them to match the vector sizes. We care a lot about dynamism. So the tiling and fusion framework here aims to support all sorts of dynamic operations. And just to mention a few challenging ones or interesting ones, broadcast, concatenation, gather, and scatter are examples that we focus on. Composition. So one very important thing is that we want to compose with existing operations and tiling implementations. And to summarize that with maybe just one example, we want to be able to fuse into existing loop nests. So if someone decides to tile an operation with SCF4, which is something that we don't do, but we would still like to be able to fuse operands into that sort of loop nest, despite the initial tiling not being done through the GmlSt framework. And then last but not least, something that we don't do today, but we might want to do in the future, is we want to be ready for other types of subsets that are not tiles. So for example, ragged or jagged subsets of tensors should at some point fit into this framework. But we didn't do that as of today. Today, the approach is when we reach that point where we end up with things like that, we tile to points, and that's our escape hatch. And now at that point, we essentially emit scalarized code again. But that is only when we run into something like a reshape or things like that. Next slide. This is another slide with characteristics that are a bit more detailed on the IR level. GmlSt works, as I had mentioned, on destination style IR. So this is an example of an element-wise operation expressed through linalg. And then there's just this init operand that makes it destination style. And that helps with bufferization later on. But this IR specifically is still SSA-based, so not bufferized. Very importantly, we separate subset computations or index computations, if you will, from the subset materializations. So that we can CSE away or canonicalize away the subset computations and then keep that separate from the materialization of the specific subset. So the example here gets a tile of size 32 by 8 at the offset ij from some input tensor LHS, and then it materializes that subset tensor into the LHS sub SSA value. Another interesting thing that is a bit different from, I believe, the current Linux implementation is that we represent subsets as one value. So we have these tile values that represent the top subset, rather than passing around all those indices separately. And the reasoning behind that is subjectively is it makes the IR a bit more readable, but it also makes things a bit more future-proof. In case we want to have other kinds of subsets, we can just pass them around as one value. Next slide. Yeah, this is where the examples start. And if any of you care about one very urgently, we can jump to that one. Otherwise, I would go through tiling and fusion element-wise ops, which is the very straightforward and probably simplest case of all of them. And then if we have time, we could dive into concat. And the others, you get the slides, you can dig through them yourself. If you have questions, feel free to ask them. Cool, then let's do tiling and fusion of element-wise operations. This is the input IR, this is MHLO. This is not even a destination stylus of this point. It's just an addition followed by a multiplication. And it doesn't even really matter what we add and multiply here for the sake of the example. It's just two subsequent element-wise operations. So what we'll do is we'll tile the root operation, the multiplication, and then we will see how we fuse the addition into the existing loop nest. Next slide. This is the same as before. In green, by the way, is whatever is actual computation based on data. Blue is index computations, and yellow is materializations. This is essentially the same as before, except that it is now in destination style. The dynamic map is an element-wise operation, addition and multiplication. This is shortened IR, so it's a bit. It's not. It wouldn't run, but it gives you the idea of what's going on. And outs gives the inner tensor, and that's what makes it destination style IR. Next slide. So you see here is the second operation, the multiplication was tiled, and it's been tiled to a parallel loop that loops over the individual tiles, and does that with step 4 and 8, which means that it aims to get tiles of size 4 by 8. And then the first thing we do is we compute the tile at the offset ij, and the size is intended to be 4 by 8, but because the initial tensor is of dynamic shape, it can actually be smaller. So the TD0, TD1 are values that have to be computed. They will in most cases be 4 and 8, except for the remainder at the edge of the tensor where they can be smaller. So they will be in the range of 1 to 4 by 8. And with that tile, we can actually use this one tile computation to materialize all the operands and also the subset that we want to insert into. And we do that by materializing the subset that we care about, namely the tile, based on the operands AB, C, and init. And then we have the smaller tiled version of the element-wise operation, which is the multiplication at the bottom. And we yield that into the init tensor. So what that means on tensor-based IR, it means that we take this init tensor as initialization values, and all of them will be overwritten in this case, but they're the initialization values. The parallel loop is a GmlSt parallel loop that yields subsets into certain areas of the tensor. And if there's no accumulator defined, which is the case here, it assumes that they're all disjoint, and it will collect all of these subtiles and patch them together into one big tensor, and that is the result ABC. And that allows us to express in the IR here is to express all the different tile computations completely separate from one another and maintain destination style IR. So the GmlSt parallel loop is by itself destination style as well. Next slide. This is the fusion step of GmlSt, is the fusion step. We've fused the addition operation into the existing loop nest. And that is based on an interface implementation of addition. So the addition has been told that the subset that we care about is tile, and because it's an element-wise operation, it knows that if we care about tile, it will care about the same subset for its operands. Because it's element-wise, it's a very simple fusion here. And what that results in is that we materialize all the individual operands A, B, C at the requested tile. We do the first operation on that tile, and the second operation on that tile, and we yield it into the init tensor. We yield that subset based on the init tensor in this loop iteration, and the result is the same as before. It's a semantics preserving transformation, but it's all tiled. And when we bufferize this, what that will resolve into is that it will take the buffer that is associated with the init value, and it will just write the results into that buffer instead of creating a new one. Cool. I believe this is the tiling and fusion of element-wise operation, and we're at 15 minutes. So maybe we can have a quick look at Concat. Next slide. Because Concat is a nice example that shows how we use materialize ops as an entry point diffusion, and that allows us once to be independent of the specific loop types that we have, and it allows us to fuse into if statements, into switch statements, into all kinds of different loop types. And fusion is basically completely independent from the loop type that we're looking at, or the control flow that we're looking at. Next slide. This is, again, concatenation in destination style. It's not surprise, it's just like before. It has an init operand, and it concatenates two tensors. Next slide. And this is just a tiled version of it. And because we tile it with size 1 in the concatenation dimension, we can actually lower it to an if then else statement. And here we can materialize the tile, and we know that it is of size 1 exactly. That's why it's TD0, TD1 is the size. And then we can just materialize this subtile from the operand AB, because the if statement checks that we fall into that operand. And the reason why I chose this example is because it's a nice case where you can actually tile to an if then else statement, and we will still be able to fuse into this if then else statement. Next slide. And the next slide just shows what you can fuse into it. You can fuse the AB into the materialize, or essentially dissolve the materialize and fuse AB into the loop nest and the SCF construct. Yeah, I think those are the examples that we have time for. And if you're interested in one of the other, I'm happy to answer questions, but this is where the Q&A was meant to be. Thank you.
Hello?
Yeah, hi.
So I had a question about how the tile sizes would be determined for when we do these tilings. So what was covered here was how we would tile, but different devices need different tile sizes. So how would we know to request, say, a 4x8 rather than something else?
Right. That's a question that would be answered by heuristics. And I believe we have a story for that, but that is not a part of GmlSt. GmlSt is just the framework that allows you to do that. And then on top of that, you'd have to make these sorts of decisions.
Right. But what I mean is, how would we pass those decisions to GmlSt? What the API for that would be?
All right. Okay. So I think the API in parts is a bit in flux. The way we do it, we have passes that do these sorts of things, and they're configurable with regards to the tile size that has been passed to them. I think the API there is not very stable today, but
from what I've seen so far, these values are passed in the code. So they come from the user, not from any sort of metadata, correct?
Yeah, today they come from the code. They're passed through the code, but I believe the longer term goal is to have heuristics on top of that figure these things out. Maybe Stefan wants to comment on that. I think Stefan is.
I can comment on that. So the plan is, so everything that you saw now is about mechanics on how to do tiling and fusion. But you are right that the tile sizes will be different depending on the platform, depending on what the operation you want to tile, and many other details. And all of that needs a layer on top, which will be like an additional pass before you actually start tiling and fusion, which will drive fusion and tiling decision based on some cost model, which will evaluate how much memory you need for the kernel, what vectorization instructions are available, and so on.
Right, but that's kind of not my question. My question isn't where we get the tile size. My question is how we pass it to GmlSt, what the plan is for that.
Right, to pass it to GmlSt, we will either use a transform dialect, which can also pass all the parameters to all the passes, or we will have the similar version implemented in C++ like we do now. So all our passes have options, and that's how it's driven.
Sorry, just on top of that, I have a question. So in that way, like, do you at least plan or like see finding out what are the different, like, you know, sizes available, like essentially exploring the devices available in your system? Or like, do you expect that to be passed by the user as a compile argument?
So there is a team in Paris that explores how you can actually run a distributed pipeline that will try different parameters for, let's say, I don't know, matmul kernel and find optimal ones. And that can be used. That's one of the approaches. Another approach is to have a really nice cost model, which will have some high accuracy, like that will predict the runtime of the kernel. And depending on that, you can optimize and find the tiling sizes.
Maybe another thing to clarify.
Sorry, what about partial tiles? Since you had dynamic shapes here, for some sizes, it may actually need partial tile loops. So we have a representation for that as well.
Frederik, do you want to answer that?
Well, yeah, I mean, the tiles that in the examples, they were partial. They had dynamic size, and so in most cases, they will be the tile size that we chose, but for the edges, they will be smaller. And the code that we generate is able to handle the dynamic case. And we have some smarts in it that figure out cases in which it can prove statically that it is perfectly tiled, and then those things disappear. But we are able to generate code that handles this sort of dynamism.
So even the fusion may not be valid in some cases for a particular target. If you use certain tile sizes, for example. So how does that? Is that the caller's responsibility to make sure that for the dynamic sizes possible, it will not run into problems?
Yeah, I mean, if you generate, so if we generate tile sizes that are not, I'm not sure if I understand the question correctly.
So let me give you an example. Let's say on a GPU, there's a shared memory limit. So there may be some sizes for which fusion may not be valid. So you'd have to run the unfused version of the code instead of the fused version.
Right. I think, yeah, if you instruct GmlSt to generate tiles of a certain size, it will just do that. And if that happens to be illegal on the device you run it on, then it will break. Yeah.
I see. Okay. So it's really okay.
But so for example, when we generate vectorized code and we end up with static sizes or with sizes that are not static or not vectorizable, it will just not vectorize them, and then it will like either we tie them to scalars and we get away that way, or we end up bufferizing them, and then so there are few possible escapes in the case that we're looking at the moment, but also that's not ideal, and you just have to choose the tile sizes the right way. Yeah.
So maybe also something to add, because there were quite some questions around this. So GmlSt is just one component of a compiler, right? It doesn't form a compiler in itself. It's essentially the mechanics we use to express these tilings and to be able to co-generate them, to perform all the structured operations required. But you will need a compiler that does versioning or drives this or any of that, right? So this is just the mechanics of how to do fusion in IR in a reasonably generic way, that you don't have to kind of do this for every use case by hand again.
All right, I think, yeah, we have one final presentation from Eugene. And just to make a note, we don't have so much time left. So what we might do is present Eugene's presentation, add the video to GitHub discussions and continue the discussions there. So Eugene, take it away.
Yeah, thank you. I'll basically give a short overview of how XLA Runtime plus Cuda Graphs could work, and it has some basic implementation right now on GitHub, and it works end to end. And the next slide. So the idea that in XLA today you can always, the XLA modules always have one entry point and one function. There is no such limitation in XLA modules when you go compile to the XLA runtime. So for example, you might export multiple functions from the single XLA module. So in this example, I can export add and multiply, and these functions, they are callable through C++ API. So you can compile XLA program and with multiple functions, just right like a regular C++ module. The next slide. And what's nice about these functions and XLA runtime, that you can pass a reference to a function to your custom call. So in this example, we have the callRef custom call that takes 2 arguments, 2 tensors, and at runtime it's mapped to callRef custom call implemented in C++ handler. So on the left you can see the binding, how you bind C++ function to a custom call. So it takes 2 memref arguments and a reference to a function, and it just calls the function passed as a reference with arguments. So we have an implementation function that implements the behavior. So it is just an MHLO add in the function body, it's impl. And if you take a look at main function, so we can call like regular MLIR function call. We can call a callRef custom call with 2 arguments and pass a function to the implementation, and then it will be serialized, and at runtime we invoke the custom call handler, and then we can add any behavior to these functions. So the next slide. So the idea that we can use this mechanism in XLA runtime to build multiple kinds of functions inside the XLA module. So in addition to the main function that basically right now, all XLA operations, they are eager. So once you execute MHLO add, you immediately submit fusion device kernel to device stream and execute it. But with the new runtime, we can outline multiple types of functions that basically graph construction. So in this example, the first function, graph capture, it looks like a regular XLA function, but when it is lowered to LVM and basically to executable, it's not eagerly executing MHLO add operation as a device kernel on the stream. But what it does is just capturing this add as a node on the Cuda graph. So On the left, you can see the custom call binding for the graph launch. So we get all the arguments and we get a reference to a function that captures the graph. Then we can do the cache lookup, caching for performance. If we see new pointers passed with the arguments, then we capture the new Cuda graph using the graph construction function and instantiate a Cuda graph executable and run it. If all pointers are the same, then can we use existing Cuda graph. So in the main function on the right, so you can see we call the graph launch custom call, and we pass a capture function by reference plus all the arguments that we want this graph to run. And the runtime is responsible for making sure that graph is instantiated and performant. So in XLA today, I've seen some branches from last year when people tried to enable Cuda graphs for XLA. But the attempt was to enable Cuda graphs for whole modules, so all or nothing. And in XLA, there is no guarantee that pointers will not change from run to run. And especially, it's hard to guarantee that inputs will not change. But it's much easier to guarantee that temporary allocation, basically all the temporary values inside your program. You can basically allocate your temporary allocation and keep it around between different runs, and then you can guarantee that your pointers are stable. Also, with this approach, we can outline loop body into a graph capture function, and we can statically, for example, verify if the loop body is large enough and the loop iteration count is statically known to be larger than some size. It is relatively straightforward cost model to figure out is graph capturing beneficial or not. And even if pointers are changing from run to run of the XLA model, the pointers inside the loop body, they are guaranteed to be the same. So it is relatively easy to outline that in the graph capture function. So the idea that we don't have to outline all or nothing, we can have a relatively simple cost model that identifies what is beneficial. So right now it is implemented and available on GitHub, but it is proof of concept. Doesn't do any caching. It instantiates new Cuda graph on every launch, so don't expect to see any performance benefits. And it only supports running sequences of device kernels, but we want to support codegen and cuBLAS and so on. Also, we are not constrained to only graph capture, like stream capture. We can do explicit graph construction with nodes and graph updates, because we're not constrained by HLO. So once we get from HLO to some kind of runtime dialect, we can represent way more explicit things. And it is hard, well, it is impossible to add codegen and cuBLAS calls explicitly, but we definitely should be relatively easier to support device kernels. And presumably we should be able to update captured graph, constructed graphs with explicit graph update functions when pointers changing. Yeah, and I think that's all for Cuda graphs. You can take a look. Let me send the link. I don't think that the link is working in the presentation.
Yeah, I was just going to ask for the link. Yeah, I'd like to see if we can get hip graphs working with that as well. Thanks.
Yeah, thank you so much, Eugene. And just a reminder, we're going to cut Q&A here due to time, but we will publish this presentation on the video on GitHub discussions, so we can continue the discussions there. One very small note that I wanted to make, you may have seen the OpenXLA logo in the bottom left corner of our slides here. That is a new logo that we recently came up with, and hope you like it. Hopefully swag will be in short order as well. Great. Thanks, Stefan. All right. I think we had a couple of other presentations, maybe just a quick overview of the updated roadmap of migrating XLA from TensorFlow to OpenXLA. We can also post that on GitHub discussions and continue the conversation there as well. So yeah, I want to encourage everyone to continue chatting on GitHub discussions, Discord, the relevant issues and PRs we mentioned today, just to keep the conversation going until the next community meeting, which will happen in a month on the third Thursday at 8 a.m. Pacific time. So thanks everyone for joining us today, and look for the slides and videos tomorrow.